Okay, so thanks a lot for the organization and for having me. So I'll be talking about a paper that appeared earlier this year on bounds on quantum evolution complexity from lattice cryptography with my collaborators listed here. So, okay, let me see how to do this. All right. So complexity has appeared increasingly in discussions of black hole physics in recent years. It has been conjectured to compute the volume behind horizons of black holes. It has been related to the difficulty of reconstructing black hole interiors and to the protection of causality, and also to the difficulty of distinguishing black hole microstates. Now, a lot of the work on complexity has been on proposed gravitational duals, and we really need tools for computing complexity in quantum mechanics or ideally quantum field theory. Another motivation is the question what causes black holes to be complex. It has been suggested that chaotic time evolution might be underlying this. And so one natural question to ask is whether complexity can distinguish chaotic from integrable evolution. And that's a question I will address in a specific context, which is actually not directly related to holography in this talk. So I will start introducing the bound we derived on complexity. Then I will apply it to a couple of classes of systems, and then I'll conclude. So let's talk about the complexity of time evolution. In circuit complexity, people refer to the minimal number of simple gates or simple operations one needs to perform a quantum computation. And Nielsen has quantified this in geometric complexity. Namely, he proposed to look at the shortest path in the manifold of unitaries between the identity operator and the unitary operator of interest. So it takes some unitary u of t, which we call u target, compute the length of geodesic between the identity operator and that unitary. So for this one, obviously needs a metric, and the simplest possibility one can look at, which will actually turn out to be too simple for our purposes, is the bi-invariant metric on the group manifolds. So one can introduce velocity v defined in this way and expand it in a basis of Hermitian generators, where normalized as follows. I hope you can see my pointer. And in terms of this, the so-called bi-invariant complexity would be the minimum of this distance written in this way, which can be written in components as follows. Now, when it will turn out that we need a more sophisticated metric, because when talking about complexity, it's important to distinguish between operations that are easy to perform and ones that are difficult to perform. And the easy ones will often be associated to local operators, and the hard ones to non-local ones. So one introduces a complexity metric by looking at the tangent space of the manifold of unitaries and splitting the tangent directions into easy and hard ones. The easy ones are denoted by indices alpha, the hard ones are dotted. And one introduces a cost factor mu that gives a bigger penalty to the hard directions. So the expression for the length of a curve on the manifold of unitaries is modified by this factor mu. And in components, it takes the following form. So for mu equals 1, it was reduced to the bi-invariant complexity. And usually one chooses mu to be of order the dimension of the Hilbert space, which I will denote by D in this talk. And one always chooses a notion of locality in such a way that the Hamiltonian itself is always considered a local or an easy operator. And the goal of this talk will be to characterize the complexity of time evolution or of this time evolution operator for integrable and chaotic models, and to see how this notion of complexity distinguishes between the two. All right, so first let's go back to the case of bi-invariant complexity. So in this case, everything becomes very simple. The geodesics in the bi-invariant metric can be checked to have constant velocity v. So they take the following form. They're just exponentials of ivt with v, a constant matrix. And the geodesics connecting the identity operator with the operator of interest then takes the following form. Exponential minus I h prime t, where h prime again is a constant matrix. So in order for these two paths to agree at time t, we need to impose the following condition. And in the simplest or the generic case where there's no degeneracies, this relation implies that the eigenvectors are the same between h and h prime, and that the eigenvalues are related in a simple way, namely by integer shifts of, or essentially integer shifts of the energy levels. So these are the h primes that characterize the candidate geodesics to be the shortest one. And so if you compute the complexity, you just minimize this length over all possible choices of h prime. If I write it out, it takes the following expression. And it's a very easy exercise to solve this. Namely, one chooses the integers kn in such a way that this combination is between minus pi and pi. So in other words, you obtain kn by rounding ent divided by 2 pi. So let's look at early time complexity, and then we'll move on to late times. So for early times, it's clear that so when ent or when t is small enough, it will be most profitable to choose all the kn simply equal to 0. And in that case, the early time complexity is simply proportional to t, with a normalization factor that we will set equal to 1 by rescaling the spectrum of energies. And to be precise, we will also shift the energies in such a way that the trace of the Hamiltonian vanishes and the trace of h squared becomes equal to 1. So with these conventions, the early time complexity is universal. It's just C of t is equal to t for all physical systems. And this actually continues to hold if we work with a complexity metric with a penalty factor mu. I should make one note for the experts, which is that the conventions we are using differ by the conventions used by Nielsen by a factor of the square root of the dimension of the Hilbert space. But don't worry if you're not familiar with the standard conventions. All right, so let's now look at the late time bi-invariant complexity. So the early time behavior has to stop at some point because the manifold of unitaries is compact, so you cannot get arbitrarily long minimal geodesics. And in fact, there's a simple argument to say that at late times, this will saturate, and we can actually even infer the saturation value. The idea is that, or the intuition is that, let's assume that a generic point along the line ENT is as close to a lattice point as a generic point in space. And it turns out that if you look at the distribution of points in space and the distribution of distances to the lattice, that this localizes in a high dimensional Hilbert space, and it concentrates around a certain value. And you can also compute the variance from the simple assumption, and both the height of the plateau and the variance agree very well with the actual numerics. Now, this was all very nice, but the problem is that the plateau height is too universal here. It doesn't distinguish between, for instance, chaotic and integrable dynamics of the system. So it's too universal for our purposes. There may be some subtle distinctions in the transient behavior, but let's not dwell on this for the moment. And I should note that we're ignoring Poincare recurrences at extremely late times, which are in practice unmeasurable. So here is a plot of the complexity in the bi-invariant metric. So here at early times, you see that the saturation is around the same value. It's just that the integrable model that we looked at has a bigger variance, but at sufficiently late times, the variance doesn't distinguish anymore between integrable and chaotic. So this is just a plateau height that is quite universal. All right, so let's move on to the complexity metric. So we're introducing penalty factor mu. And it's hopeless to actually compute the geodesics using this complexity metric, let alone find the shortest one. So we'll use a variational method. So what we will do is say, instead of minimizing over all possible curves, we will minimize over a special class of curves, which are the geodesics in the bi-invariant metric. And as in all variational principles, if we have to compute a minimum and we do it over a restricted set of objects, a restricted set of curves in this case, we will find the rigorous upper bound on the Nielsen complexity. So these bi-invariant geodesics, which I showed you before, and I told you they're very simple, they will generically not be geodesics of the complexity metric, but that's fine. They're just part of a variational ansatz. They don't need to be geodesics to derive an upper bound. So finding the bi-invariant geodesic with the shortest length, measured using the complexity metric, turns out to be a problem that is too hard as well. But the point of this work will be that there exists a suboptimal solution, which also provides a rigorous upper bound. And then the question will be, is this a useful bound? And I will argue that it is, in the sense that I will show that it separates chaotic from integrable time evolution. So let me give you a few details. So we start with a bi-invariant geodesic. So remember, this was simply this exponential with some constant matrix h prime, and I'm labeling it with these integers k that we had before. So instead of finding the shortest geodesic in the complexity metric, we will just minimize over all possible choices of vectors kn. Let me tell you what we will minimize. So we decompose the projectors on energy eigenstates into the easy directions with indices alpha and the hard directions with indices alpha dot. And here are the expansion coefficients. And then one can easily check that the norm of this primed Hamiltonian takes the following form. You see the cost factor mu here. And if you can rewrite it by introducing a matrix Q in the following form. So if mu was equal to 1, so if we had a bi-invariant metric, you recognize the expression, this length squared of a distance on the lattice that went into the expression for the bi-invariant complexity. Here we will correct it with some matrix QMN, which is defined in the following way. We take all the non-local generators and we take the energy eigenstates corresponding to the indices m and n, and we sum over all these non-local generators. Or equivalently, you can write it as the unit matrix and then subtract the analogous quantity with all the local generators, which is often how you compute it in practice, because usually there will be much fewer local generators than non-local ones. And the quantity we want to minimize, or actually the bound that we will find on complexity is the minimum over all vectors k of the following quantity written here. So let me give you a few properties of this matrix Q. So you can easily check that the eigenvalues are between 0 and 1. And you can also, so this shows that the eigenvalues are positive. And if you apply a similar reasoning to the right-hand side here, you immediately see that they are smaller than 1. And you can also verify straightforwardly that the vector of energy eigenvalues is a zero mode of this matrix Q. And the argument essentially relies on the fact that the Hamiltonian itself is a local operator. So if I take the in product with a non-local generator, it will vanish. And similarly, from any zero mode of this matrix Q, one can construct a purely local conservation law. So this will underlie several of the observations I will give you. Now, what we want to do is solve this minimization problem. So we are talking about a minimization on some hypercubic lattice in space. Namely, we have these vectors k on a lattice. But the metric that we're using to compute lengths is non-trivial. It's not just delta mm, but there is this correction involving the Q and M matrix. And remember, mu was a large number. It was said to be the dimension of the Hilbert space. So clearly this will significantly modify the minimization problem, that the trivial minimization problem that we would have in the bi-invariant case. Now, this minimization problem on a lattice with a non-trivial metric is equivalent by linear transformation to a minimization problem in flat space, but on a lattice that is not hypercubic. And this problem has been elaborately studied before. It's known as the closest vector problem. Namely, you take a given vector, the vector E and T in this case, and you ask yourself, what is the lattice vector that is closest to it? And it turns out that even the simplified problem is extremely difficult to solve exactly. All the algorithms that are known take in time exponential in the Hilbert space dimension, and in computer science, whenever something is exponential, it's considered impossible in practice. And actually, this closest vector problem, because of the difficulty of solving this, actually appears in models of lattice cryptography. So it appears quite hopeless at this stage to solve this. Now, what saves us is that we're not necessarily interested in the exact solution of this problem, which is impossible to get, but there exist feasible algorithms which run in polynomial time that can be used to find approximate solutions of this closest vector problem, and therefore of our minimization problem. And again, this will still give a rigorous upper bound on Nielsen complexity. So let me first give you a very trivial way to illustrate why the simple rounding that we had on a hypercubic lattice with Euclidean metric will not work if we have a non-hypercubic lattice. So let me take some skewed lattice with basis vectors B1 and B2. And let's take some vector E, which will be the analog of the vector of energies. And you can easily verify in the picture that if you decompose this vector E into the basis, it will be 0.6 times B2 minus 6 times the vector B1. Now, if I were to naively round the coefficients to integers, which is what I would do in the bi-invariant case, I would simply have B2 minus 6 times B1, but this rounded vector is clearly not the correct solution for the closest vector problem to the original vector E. And this is a trivial example in 2 dimensions. You can imagine that if you're in 1,000 or 10,000 dimensions, it becomes completely hopeless. So fortunately, there exists approximation methods that are extremely useful for us. And we will actually combine three algorithms that we took from the literature. So one is a so-called LLL algorithm, after the authors are listed here. And what that algorithm essentially does is it takes a lattice basis, which can be very skewed, into a basis that is more orthogonal one and more round. And so which is closer to what one would have in the case of the bi-invariant complexity, for instance. So that's called basis reduction. That will be the first step in our algorithm. After you've done that, you can use a so-called nearest plane algorithm by Babai. And what that essentially does is it looks at some family of lattice hyperplanes, which is spanned by d-1 basis factors. And you simply project the point of which you're trying to find the closest lattice point to the hyperplane that is closest to us. Now, nothing guarantees that the shortest vector is on the nearest hyperplane, but still it turns out that this gives a good approximate solution. So once you've done that, you repeat the whole thing in one dimension less until you end up with one lattice point, which will be the candidate for the closest vector. And then after doing those two algorithms, there's one more step that we will do, which is the so-called greedy algorithm. So once you have a candidate solution, you just try each of the d dimensions in which you can move, and you see whether you can improve the result by moving in one of those directions. And if you find at least one direction in which you can improve, you choose to go in the direction of the biggest gain. And all these three algorithms run in a time that is polynomial in the Hilbert space dimension D. All right, so that's the description of our bound. Let me now tell you how this worked in specific models. And we have first tested it on a model that was studied before, and that's several SYK models. So as you presumably all know, you start from this Clifford algebra, and you can start representations of it. The simplest models is the free SYK model. You take some arbitrary matrix Jij, and you write this quadratic Hamiltonian. By doing some linear redefinition of variables, you can write this in the following way, where the matrices J3 are quadratic infermions, and they have eigenvalues +1 and -1. And so you can immediately read off the energy eigenvalues of this free Hamiltonian as these linear combinations of the frequencies. So that's a simple free model. Then one can go to a slightly more complicated model, which is an interacting integrable SYK model, where you take the same matrices J3 and you add to the free model some quadratic combination of the J3s, which will be a quartic term in the original fermions. And this M is some random matrix drawn from a certain ensemble. The details don't matter too much for this talk. And finally, we will take a chaotic model, which is again a deformation of the free model, but now with a quartic term in fermions with random coefficients J, I, J, K, L, which are again drawn from some ensemble. So let me define what I mean by locality in this model. So we will define an operator to be local if it is constructed out of operators, or at least if it's a combination of operators that contain at most k fermions, as written here more precisely. Now, oops, sorry, let me go back. Okay, so for the free and integrable SYK models, a significant reduction of the complexity plateau height was found using model-specific methods in recent work by these authors. And this analysis relied on having many quadratic and quartic conservation laws in the system, which implied many zero modes of the matrix Q. And remember, Q was what multiplied the penalty factor. So if you can make shifts in the lattice along zero modes of Q, these do not come with large penalties. And so these authors used these conservation laws to shift in those directions, and they managed to significantly reduce the complexity compared to what it would have been in chaotic models. And what we did is blindly run our algorithm, which is an automated method, on this model. And as I will show you, we essentially recovered the results for free SYK. We significantly improve the results for integrable SYK, and we provide results for chaotic SYK, which were beyond reach in using the previous methods. So let me illustrate that with a couple of plots. So on the left, we have the free SYK model. The plot which was, or the curve which was conjectured to be exact in the previous work is the solid blue line, which is sometimes hidden behind other lines. And when we run our algorithm in full, we have the solid red line. And as you can see, we essentially reproduce the previous results for most times. And our upper bound is a bit less good at some specific, in some specific regions. You also see that adding the greedy algorithm to just LLL and bi algorithm also helps at certain places in certain ranges of time. So that's quite encouraging because we didn't build in anything specific to this model. So we also had ran it on chaotic SYK models. And here you notice that the plateau height is significantly higher than in the free model. You can compare the numbers on the vertical axis. And it does give you quite nice linear growth followed by saturation plot. And here we don't have anything to compare with. And here is the comparison of our integrable SYK models. So the earlier results was this blue line, ours was the red line, and you see that our upper bound is a significant improvement to the previous work. And we also understand what is the likely cause or what are the improvements that could have been done to the earlier work to get very close to what we found using an algorithm. So here we plot the plateau height as a function of n, the number of fermions, and so which is related to the dimension of the Hilbert space. And you see on this logarithmic plot that the slope of the green and red lines, which correspond to integrable models, is about half of the slope for the chaotic models, which are basically on top of each other. And if I divide out by a factor of square root of d to go to Nielsen's conventions for complexity, you see that for chaotic models, you will still have exponential growth in the sense that it will still be square root of d. When I say exponential, I mean exponential in, well, sometimes people denote the dimension of the Hilbert space as exponential s, where s is some entropy. So for chaotic models, it will scale as square root of d, whereas for integrable models, it will not scale as square root of d, but it will be polynomial in n. So in other words, for these models, the plateau height for chaotic models is exponential in n, and for integral models is polynomial in n, so there's a dramatic difference between the two. All right, so these SYK models we looked at are actually very special in the sense that the integrable SYK model is not a generic integrable system at all, in the sense that there are unusually many quadratic and quartic conservation laws, and these conserved charges also have integer spectra, and these are things one doesn't expect in a generic integrable system. Another drawback of these models is that they are fermionic, and fermionics do not have a conventional semi-classical limit. And that's a drawback when you want to discuss quantum chaos and integrability, because the notion of chaos is sharply defined in semi-classical regimes. So it would be really nice to have models where you can go to semi-classical limits and actually make a more rigorous contact with quantum chaos. So that's the motivation to introduce or to use a class of models that give an improvement on these drawbacks. And these are quantum resonant systems, which were introduced a few years ago. So in short, these quantum resonant systems are given by the following class of Hamiltonians. The A's and the A daggers are bosonic creation and annihilation operators. And these C's are so-called interaction coefficients, which one can choose in order to specify a specific model. Why are they called resonant? Well, that's because of the condition n plus m equals k plus l that is written here. So if you think of AL as eliminating a mode with linearized energy L, then you see that this preserves the linearized energy. So to build a Hilbert space, you construct a Fock space on the Fock vacuum using the creation operators. And if you look at this Hamiltonian, there are two obvious conserved charges. There is the so-called particle number n, because the Hamiltonian destroys two quanta and adds two. And then there is m, which is with what I call the linearized energy before, which because of the resonance condition is conserved. So now we have a bosonic model. Obviously, it has an infinite dimensional Hilbert space, but because of these conserved charges, the Hamiltonian is block diagonal. And each block associated with specific values of n and m is finite dimensional. And the whole Hamiltonian is block diagonal with finite dimensional blocks which grow in size as you go further down in this infinite dimensional matrix. And therefore, you can diagonalize this Hamiltonian block by block for as long as your computer allows you to do it. So these quantum resonant systems, actually, I introduced them in a rather ad hoc way here, but they actually appear extremely naturally as quantizations of classical resonance systems, and those appear as controlled approximations to weakly nonlinear dynamics. So for instance, if you had some free system and you added some quartic interaction with a small coefficient in front, and then you went to the interaction picture to factor out the free evolution, you would get an interaction Hamiltonian that takes the following form with some specific interaction coefficients. And the nice thing is that depending on the choice of these interaction coefficients, you can have a variety of dynamical behavior. Mathematicians discovered turbulence in this model. There's recurrences. There's versions of this model that are integrable. There's invariant submanifolds. Other interaction coefficients give strongly chaotic behavior, you name it. And to give just one example of a generic integrable model, the so-called truncated Sego model, if you set all the interaction coefficients 0 to 0, except if there is at least one zero index. In that case, you set them equal to 1. For that case, you have an integrable model. And I will show you the level spacing statistics that supports this. If one draws the interaction coefficients randomly from some normal distribution, then one finds a chaotic model. And so just to illustrate this, if you plot the distribution of normalized level spacings, then for integral models or for generic integral models, one expects a Poisson statistic because the energy levels are roughly independent. And for chaotic models, one expects the Wigner-Dyson distribution that also appears in random matrix theory, which has to do with level repulsion. And so you see that the random quantum resonance system quite nicely follows the Wigner-Dyson distribution, whereas for the truncated Sego, it quite nicely follows a Poisson distribution. And all these plots are for a Hilbert space dimension, which is 5,000 something. So now let's move on to complexity in these quantum resonance systems. So if you look at this Hamiltonian, you can see that it changes at most 2 modes in a given, for a given state in a given block. That's because it destroys 2 quanta and it replaces them by 2 other quanta. And this we can generalize to define a locality degree. So the locality will be the locality degree will be the number of modes that are changed by an operator. And so for this truncated Sego model, which we believe to be a more generic integral model than integrable SYK, we find, as I will show you, that there is a noticeable complexity reduction compared to chaotic models, but it is much less dramatic than in integrable SYK. In particular, the difference in plateau height will now not be exponential, but it will be just 10 to 20%, but it will be noticeable. So here are some plots to illustrate this. So the top plots are for locality degree 2. So there the Hamiltonian is barely local. And on the left plot, you see the linear growth followed by saturation. And on the right plot, I'm zooming in on the plateau. And you see that the blue line, which is the chaotic model, is above the various integrable models. And if we increase the locality degree, so we will consider many more operators to be local. In that case, this distinction becomes much more pronounced. You already see it with the naked eye for on the left plot. And on the right plot, okay, we zoomed in again, and you see that the chaotic model plateau value is significantly above those of the integral models. So I can also tell you a bit about the distribution of the Q eigenvalues, which I told you underlies much of this behavior. So for integral models, which are the green and the red ones on the curves, we have a tower of conserved charges of increasing locality degree. And the complexity plateau height correlates with the number of small q eigenvalues. Again, I told you that if you have a 0 eigenvalue of q, you can shift things in those directions without being penalized by the cost factors. If you have a small eigenvalue, you can imagine that you can move things while being penalized only a little bit, which also helps. I won't dwell on this in more detail, but there is a nice connection. And there are nice differences between chaotic and integral models in terms of the eigenvalue distributions of Q. So mainly, if you have integrability, you will have more local conserved charges, and therefore also more small eigenvalues of Q. All right, so let me conclude and give you some outlook. So we reduced the upper bound on Nielsen complexity to the closest factor problem, which has been extensively studied in the context of lattice cryptography. Our bound successfully separates integrable from chaotic systems. So for the case of SYK, there is a strong separation. So in terms of Nielsen complexity, it's exponential versus polynomial in the number of fermions n. For the more generic quantum resonance systems, the plateau value is always exponential, but there is a modest but significant reduction in complexity for integrable versions. And it remains to be seen whether improvements of our bound, remember that we only looked at an infinite but still very special class of curves to do the minimization, whether that will lead to a more dramatic separation for generic models. And I'm actually not quite sure if there are solid expectations for whether generic integrable systems are supposed to have exponential or polynomial complexity. It could be, if we only look at our work, that our ansatz was just not good enough to achieve the reduction to polynomial levels. It could also be that even generic integrable systems have exponential complexity. I don't know what the answer is at this point. I did learn that there were similar results by the group of Rabinovici and Zonner and their collaborators, where they studied similar questions, not using Nielsen complexity, but using Krylov complexity, and they seem to find similar behavior. A key quantity in our analysis, even though I didn't emphasize it very much in this talk, is this Q matrix. And the complexity reduction that we witnessed is related to small eigenvalues of this matrix Q. And that's something we're exploring further right now. Another thing we are working on right now is to move to spin chains. So what the SYK models and the quantum resonance systems have in common is that the only notion of locality we had to do with the number of modes involved in an operator. Whereas for spin chains, you still have that notion of locality, but there's also a notion of spatial locality, because in spin chains, you have a spatial structure. And it will be interesting to see what happens if you also explore spatial locality using these methods. And that's something we're exploring right now. There is technical complication that integral spin chains tend to come with degeneracies. And I told you in passing at the beginning that the method we used so far was, for simplicity, geared towards generic systems without degeneracies. So we had to tweak things a bit to deal with degeneracies as well, but it's possible to do it. So that's all. So let me stop here and thank you.